Welcome everybody to Archive Dives with Oxen AI, where each week we dive into an interesting research paper in AI, as well as the code that goes along with it. We do this in order to tease out any insights we might be able to apply to our own work. This week is an exciting one as it's building off of the diffusion transformer work that has been gaining a lot of steam since the demo of Sora that OpenAI gave back in March. And specifically today, we're diving into PixArt, which is an efficient implementation of a diffusion transformer. In fact, it's 10 times faster to train than previous state-of-the-art methods, and we'll dive into some numbers there. And it's really easy to fine-tune for a specific style. So today we fine-tuned it on 3 different styles. 1 was Lego City Adventures, 2 was The Simpsons, and 3 is Wes Anderson. I just grabbed a trailer of Asteroid City from YouTube, chopped up the frames, and was pretty impressed at how well it generalized to that new domain. I'm assuming that's a new enough movie that it probably wasn't in the original training data. So the first half of this dive will be going into the research paper, which I'll link to, and the second half will be running some code so you can see how to fine tune this end to end yourself on a single A10 GPU. And mega props to Raul from our archive dive community. He did the heavy lifting of fine-tuning the initial models here and even got a pull request accepted to the PixArt repo itself to get all of the fine-tuning working with Hugging Face and LoRa, which was broken when we first started, and we were freaking out a little that we wouldn't be able to do this dive. So mega props to Raul on that one. All right, so this paper is PixART-α, and there's a nice github.io page that goes along with it with all of the code and some pretty cool examples here. So you can see the quality of these images are extremely high, look kind of Midjourney-esque and have the ability to generalize to a bunch of different styles. But when the key innovation here is they make this diffusion transformer extremely fast to train. So what does that mean? Well, when we think of text to image models, we usually think of millions of GPU hours to get these things to work. This gets expensive fast and honestly hinders the community's ability to innovate on the models themselves. And so how much faster are we talking? Well, for reference, stable diffusion takes about 6,000 A100 GPU days and costs about $300,000 to train. And PixArt takes 12% of that training time, saving nearly $300,000. And to give you a benchmark against even newer models than that, DALL-E 2 is estimated to cost about $2 million. There's one called Raphael that I actually haven't seen, but they were referencing in this paper those 3 million. And you can see the initial pre-training for PixArt-α is about 28K. So big improvement there. And they also compare the CO2 emissions. It's pretty similar graph, so I'm not going to show it here, but saving energy while saving money, those are 2 great axes to optimize on. And if you do the math on, what did I say, 6,000 GPU hours and 12%, that gives you about 753 GPU days for this to train. And concretely, if you split that up on 64 V100s, they said the pre-training took 26 days for this whole thing to go. And while this is a huge improvement, I'm expecting that most of you don't have 28K laying around to train a model from scratch. So luckily, they did a lot of the heavy lifting for us and open sourced the model weights and the code, as well as code to fine-tune it in a parameter efficient style using LoRa, which is what we're going to dive into today. And the LoRa fine-tuning actually only takes about 3 hours and not that much data to get good results. So why would we fine-tune in the first place is something that I like to ask myself before we dive in. And the first thing is a lot of these text to image styles kind of have a noticeable style as you go in. So I'm sure when you see generative images on the web, I kind of have an eye now for if that's Midjourney or that's Dolly or that's Stable Diffusion. You can kind of see their base style that they always inject into the models. And so I wanted to start by using this prompt right here. Beautiful lady, freckles, big smile, blue eyes. This is just one of the prompts from the paper itself. And you can see this is what the model generated just by purely giving that prompt. I tweaked the prompt to say image in Lego City Adventure style, and then just concatenated the rest to see what a pure prompt engineering approach would do. And that gives you the image in the middle, which is Lego-y, but not quite what we want. And after collecting a couple hundred images, fine-tuning it, and giving the same prompt, we get something like the image on the right, which is much more detailed, or the style of image that we want here. And so I actually took all the prompts from the paper that they had in the back, everything from that beautiful lady with freckles to a teacher explaining in a fun, interested way physics to a group of interesting kids, and did 4 different variations of that. So the prompt against the base model, the prompt with the trigger phrase against the base model, which in this case did give you Lego-y type images. And then these two on the right are the LoRa base image without the trigger prompt, and then the LoRa image with the trigger prompt. So here you can see same physics teacher teaching Lego kids. And a lot of this data that we fine-tuned on were images of the Lego characters more close up and more in detail. So you can see while sometimes it does, pure prompting technique does give you Lego style, this one really gives it in the distribution of our training data. This only took a couple hours to fine tune. And while the prompt engineering approach is always faster, if it takes a couple hours on an A10, that's like $2 of compute. And I think is pretty exciting to imagine what type of content you can create by simply spending $2 for that. So diving into the paper itself, how did they get all of these speed ups? So this paper builds off of the diffusion transformers work, as well as uses Lava to perform some synthetic data generation. We've covered these topics in previous dives, diffusion transformers and Lava, so we won't go too deep into that today, but they call out 3 core design principles while they were designing PixArt. The first one is decomposing the training into 3 steps. So the first one is learning pixel level distribution of natural image. The second is aligning a text transformer and an image transformer, kind of connecting them together. And then the third is image aesthetics alignment, which is kind of what we did with the fine tune there of making it work really well for Lego characters. The second design principle, besides decomposing the training steps, is implementing this efficient transformer where they both incorporate cross attention from the text encoder to the diffusion transformer, as well as they removed a lot of the MLPs from the end and modified it to have like one massive add a linear layer at the end to reduce parameter count. And the third is just better data in general. So they use synthetic data from Lava to recaption a bunch of images in some of the classic text to image datasets. Classic meaning they came out in the past year or two. But we'll see some examples there of how the better data improved the model. So let's talk about the training steps first. So 3 steps here. pixel dependency learning is the first one. And they actually start with just using ImageNet itself to pre-train a diffusion transformer. And they take advantage of the class conditional image generation. If you're familiar with ImageNet, it's a bunch of images and their classes. So basically, when they do this first pre-training step, they are just purely training a classifier on ImageNet with a diffusion transformer and feeding in that class label as they're generating the image. The second step is they then take that pre-trained model that was pre-trained to generate ImageNet images, but just off of like a single category. And they attach a text encoder to the model to be able to transition from just generating an image from a pure class label, so just giving it the word cat and generating a cat, or the word bird and generating a bird, to giving it a full sentence and having it generate that sentence. So what they do here is they have your standard transformer block, and they take a T5 text encoder that they'll feed the text through. Then they use cross attention from all of the features that come out of the text encoder to all of the image patches in the image, and kind of inject that information directly in the in this layer right in the middle after the self-attention layer. And then they make it really fast by stripping out a lot of the intermediate multi-layer perceptrons and kind of putting them as this shared one at the end. So sorry that this image is so long. I wish we could see all of it at once, but that's the main idea there. The language model they use is specifically this 4.3 billion parameter Flan T5 double XL, and then the diffusion transformer is DiT XL2, which means just a image patch size of 2. And they fix the length of the actual prompts to 120 tokens, which they say is larger than some of the previous models, like Stable Diffusion have a context window of like 70, and they bump that up to 120. And then the final step, once they have this T5 text encoder and the cross attention module communicating all the features from the text and the image and combining them, they fine-tune this model again on high quality aesthetic data. And they say that this step converges significantly faster than the pre-training steps. So it's kind of this 3-step process. 1, pre-train it on ImageNet, which somebody else did before this work. 2, inject the features from the T5 encoder. And then 3, collect a massive data set and train it again on higher quality text to image pairs. So being the team at Oxen, we also agree that data quality is almost always the secret sauce. And in this case, they use synthetic data to improve the data quality. So what does that mean? Well, they call out certain data sets, such as the Leon data set, as having a variety of different issues. 1 is just pure text to image misalignment. 2 is deficient descriptions, and 3 is infrequent diverse vocab usage. So concretely, what that means is you have images like this that are in the Leon dataset. And so you might have like this one in the middle here of this guy working on a workbench, and the caption that was extracted from the massive web crawl was just like AH1370/1950 Saudi Arabia Gold 1 Guinea. Not very descriptive here, right? And the reason it's not very descriptive is this initial web crawl was purely taking alt tags from the images on web pages and pairing them with the image that was downloaded. So very efficient way of collecting a lot of data, but not super high quality data. So what they did is they took Lava, which is an image to text model, and they just gave it the prompt, describe this image and its style in a very detailed manner. So not that crazy of a prompt and not that crazy of a pipeline, but you can see it gives pretty high quality descriptions of the data here, and it gives you a lot more diversity in the vocabulary that's used. So like what science says about pureed tea, and versus this image features a close-up of tea with a saucer on a wooden table, the tea is described, et cetera, et cetera. So this is what they did on the Leon data set, and they actually took a few more data sets and combined them together to make their massive, more descriptive pre-training data set. The other things they note is that Leon, so these images right here, actually aren't that diverse as well. They say it's mainly product reviews from shopping websites because it was a web crawl. So instead, they augment it with the segment anything data set from Meta. We went over that paper a few months ago as well. And they run all of these images through Lava to get captions. They also grab this database called Midjourney DB or Journey DB that is 4 million Midjourney image prompt pairs and 1 million captions. So these are, you can say they get a lot of their style from Midjourney as well as just this segment anything data set. And they did some stats on the nouns that actually came out of those different subsets of data. So what they did is they looked at the statistics of noun concepts within the different data sets. So they defined a valid distinct noun as a noun that appeared more than 10 times in the data set. And then they defined distinct nouns as just how many distinct nouns there are in the data set. So what they're saying here is they want a lot of different nouns and they want them to appear 10 or more times. And so the Leon data set by itself, if you take that ratio, has about 6.4 nouns per image. And then if you recaption it with Llama or Lava, that gives you 20.9 nouns per image. Then the segment anything images are more diverse images than just products and from shopping websites. So they say that even gives you more diversity in the nouns that are appearing in those images. And then finally, this internal one is just this Midjourney data set. So wide variety of images here. And that amasses to a total, I thought I had the total data count somewhere in here. Yeah, here we go. For the 3 training steps, remember there's the ImageNet pre-training here. There's the text to image alignment, which they use the segment anything data set. And then there's the high aesthetics training, which is on the combined high quality data. So ImageNet is about 1 million images, took about 88 GPU days. The text image alignment is 10 million images from segment anything, and that took 672 days. And then finally, they do the high aesthetics training, which is combining the Midjourney data set with everything else. And that's 14 million images. They do 2, or I guess 3 variations of the high aesthetics training. one at 256 by 256, one at 512 by 512, which is what we'll be doing, and then one at 1024 by 1024. So any questions so far before we dive into how we fine tune this ourselves? So let's dive into fine tuning. So I put all of this data and the code for it in this PixART's results on Oxen. So all of these are from the paper themselves. So if you look at, let's find the PixART-α paper here. And scroll down. I literally went through every image that they have in the paper and took the caption at the bottom as just some starting point for images that we can generate. They have a ton in the back as well. I think there were 100 total in this paper. Let's see. They even call out some that don't work very well with the base model. We can get there. Here we go. So basically took all of these images and their prompts and put them in a starter data set here, and we can kind of page through and see what the model likes to output. Some pretty high quality images, pretty fun, do have kind of a mid-journey style to a lot of them. So this is just like our baseline of what the original model does. So the next step that we're going to do is we ran 3 experiments. So let's start with the Legos one itself. So what we did, or what I should say, what Raul did from our community is he took a bunch of Lego City Adventure images, and they look like this, just like frames from that movie. Some of them are of buildings, some of them are like close-up of Lego characters, like this. And basically the first step is just to run all of those through Lava and caption them. So one thing that you'll notice while doing this training is that Hugging Face requires like all of the images to be in the same directory, and then this metadata.jsonl kind of at the end of that same directory. I don't love that format just because it's hard to find the actual annotations within there. But basically for each image, we got a caption out that's pretty descriptive of what is in the actual image. And we didn't have to go manually label any of this data. We could just grab random image frames, run it on Lava, and get some metadata out. And then there is a repository called PixArt that we talked about earlier that Raul even made a pull request to go into, and pretty much all you have to do is run this accelerate command, which I'll document in our blog afterwards. And you just have to give it the path to the pre-training dir and the path to a pre-trained model, which they do have all of the models released on Hugging Face. And you kick that off for about 3 hours, and you will get out something that is able to produce results that looks like this. So in this case, these are the 4 columns that I showed you before. These are all the prompts from the back of the paper. And let's look at some individual ones. So little girl with red hair sitting at a table, portrait, Kodak portrait, I guess. This is with the trigger prompt. This is the LoRa fine-tuned without the trigger prompt. And then this is the one with the trigger prompt. Here's another one that's like Oppenheimer sits on a beach chair watching a nuclear explosion. So here, and then this is Lego Oppenheimer watching the explosion. So last night, what I decided to do was take all of this all of these steps and put it in this PixArt tutorial repo. And I thought it would be fun to just take a video from YouTube, see if we can chop it up and see how well, one, Lava can caption it, two, how well it can generalize to a video that's like not in the training distribution. So this Asteroid City movie came out, I think, definitely after ImageNet, probably after that lay-on crawl, and might be in Midjourney, but it's just hard to say if it's in that data set at all. But it has a very distinct style here, right? So the first step that one would do here is just purely extract the frames from the video. So this is just like a really simple OpenCV script that'll go through and grab all of the individual frames from that video. So the first step here is just generating this images.jsonl file that has like an index and a frame number. And you can see it's just grabbing every 10th frame from the video here. And there's actually not that much diversity in this video. Like we have, I don't know how many frames in a row, 1, 2, 3, 4, 5, 6, 7, that are all pretty much Asteroid City and that train going through. And there's only 344 images in this full data set. So then the second step is to caption all of those images using Lava. So just like the prompt in the paper, we go through and say, describe this image and its style in a very detailed manner. You can just grab one of the off-the-shelf Lava 1.5 billion models, run all of those images that we just extracted from the YouTube video through them, and then save them out with their captions. So that generates this image captions data set. And you can see we have this image, and it says the image features a gas station with a variety of vehicles parked around it. There's 2 trucks, blah, blah, blah. I thought these ones were kind of interesting. The like ones with text on them. This image is a promotional advertisement for the company Comcast. That's clearly wrong. Showing their focus on features, blah, blah, blah. It does say the word focus is written. But there's some frames in here that definitely aren't Wes Anderson-y, but the majority are, and you get a pretty detailed description out of it. This step to caption with Lava takes about 3 to 5 seconds per image, so isn't the quickest thing to generate synthetic data, but you can extrapolate through. Took about half an hour to an hour to generate it for all of these frames. And then finally, you have to convert that to the Hugging Face training data format. So you have like all of your images in this directory, and then at the end, you'll have a metadata.jsonl file that's basically just an internal server error. Just kidding. It's basically just a caption and the image itself. And then once you have that, you can basically clone this repository into your working directory. You can launch a job. They like to use this accelerate framework from Hugging Face, but you pretty much just give it this PixArt train scripts, train PixArt LoRa Hugging Face script. You give it a pre-trained model, and you give it the training data directory as well as an output directory for you where you want to store your model. That took about 3 hours, and I was actually expecting it not to work very well for a couple reasons. The first one being we don't have that big of a variety of images, and second, we have these black bars kind of at the top and the bottom. Initially just did this to make the images square and see how the model would react to having black bars at the top and the bottom, but like a much smaller image in the middle. But I was surprised when I woke up and saw the results of the images through those same prompts that we used at the start. And boom, you get something that looks super Wes Anderson-y at the other end. And not only Wes Anderson-y, but like in the style of Asteroid City, which is a newer Wes Anderson movie, right? So here is that. Oh, I guess that's a bird. I thought it was going to be the cat walking through. What's the prompt for this?
That's a new contender for Cameron.
There we go. We'll have to get you a Wes Anderson cat. But this says a very colorful and beautiful and colorful bird, cute dragon creature, professional. This is a wild prompt. Kind of confusing, actually. I thought the Oppenheimer one was pretty good as well. So this is the base one, and then this is the fine-tuned one. The faces definitely need some more work, but like the fact that this was 300 frames from a video that I just downloaded from YouTube, and it learned to put the black bars here, and it learned this style was pretty impressive. Any questions on this process or training data collection or anything so far? Cool. So I think this is really cool that like, honestly, I think end to end last night, this took me 2 hours to set everything up and kick off the train and wake up to this. Next up, we're going to extend this to give you a little more control over the images. So if you guys are familiar with ControlNet, it allows you to give key points within the images, whether that be edges or whether that be a human pose or something like that, to kind of give you finer grained control over the model results. And I think it would be really cool to like have this style, but have it be within a control net so that you could even take like a video of yourself, either have pose estimation or the canny edges running, and then generate a full end-to-end video that's hopefully coherent along with the video that you gave it, but in the style of Legos or The Simpsons or Wes Anderson. I guess we didn't look at the Simpsons one yet, but that one was interesting as well. So that same redheaded lady at the start turns into a Simpson style character. Raul,
Wow.
did you make it to the call?
Yeah, he's here.
Anything you want to add in
Yeah.
terms of the pre-training steps?
No, I think you covered it all. I did some tests, quite some tests before getting to these results. And the parameters that I found to work good with these sets that are like 400, 500 entries big are the ones that you use. So at least for LoRa training and with this kind of data sets, especially the learning rate had to be quite high compared to other fine tunings or general learnings.
Yeah, so we only had like 300 images. So what was the one that it started with? Do you remember? And what did you bump it up to?
-6. So one E -6, and then tried with -5. Even with -4, it didn't work. Or it started working, but not so good. But then with 3 E -4, it started giving the results. But this is quite a high learning rate.
Yeah, definitely. And then did you play with the rank of LoRa as well?
Yeah. So higher ranks did better. Starting with rank 8, so 8 and 16 were quite similar results. Lower were also, well, yeah, they didn't give so good results, which I think it makes sense because generally the model is a smaller model than SDXL, for example. And then training only a part of that, it ends up training just a couple of parameters. So this is why a rank of 8 or 16 obviously does better. Yeah.
Yep. Totally makes sense. And then I guess you did some experiments with stable diffusion as well. Some stats you gave me, like PixArt had 800 million parameters. Stable diffusion has like 2.5 million. Any interesting findings there you think would be fun to share?
I tried to, well, I did some fine tuning with the same data sets, or at least with the Lego one and the Simpsons one. And using the same parameters, it took about the same time, so about 3-4 hours, but the generated images were definitely not as good as using PixArt.
Yep.
Yeah.
I wonder if that's because, you know, there are more parameters and we're only applying the LoRa to a subset
Yeah,
of them or something.
I guess, yeah. So trying stable diffusion with the parameters from the script above ended up training about 0.88% of all the parameters, which is obviously quite low. So, but the point that my test was not to try to get good results with stable diffusion necessarily, but rather see with the same parameters how it compares to PixArt fine tuning.
Totally.
Yeah.
Awesome. Scott, was there another question?
There's a couple in the chat. I'm gonna-
Did Keshop's question get answered? The one, or did Raul, did what you just described answer Keshop's question about QLoRa?
What was the question? QLoRa. No, I
How much of a
didn't.
difference will there be if we use QLoRa?
Is
I
that built
didn't
into
do.
this
I
repository?
don't think it's built. No.
So that'd have to be an extension that we would make to this repository to test it, but that's a good question. Has anybody used
So
QLoRa for fine-tuning images? Or maybe Raul, you have a thought?
I tried here Dora and RS LoRa, but I didn't see too much of a difference, I guess, because the data set is too small. From what I saw on the internet, Dora applied to a standard as stable diffusion fine-tuning should give better results, but they used also different data sets.
Got it.
And then
Cool.
there's additional questions from Kaiser and by Bob. Kaiser said there's a 1024 by 1024 version of this model as well.
Yeah, there is. We use the 512 by 512. Raul, did you try the bigger one? I don't know if it would fit on the A10 or not.
No. Well, most of it, I did it on my own machine, which had only 16 gigabyte, and it was using a total of like 14 to 15, depending on training and what other apps I was running. So
Yeah,
I
do you want to
couldn't
tell
run.
the story about your Windows UI taking up some RAM?
Yeah. So at one point, doing the same test, it started running out of memory, which was funny because I didn't change anything. And then I found out that a lot of applications, especially Chrome, was running, and closing all of them just reduced the usage with like 2 gigabytes. So that's if you do fine tuning or training on your own machine, just make sure that you have as little or not too many apps running at all.
That's funny. Be wary at home, training at home. Um, and then what would be the ideal fine-tuning data set size for optimal results? That's a great question. I mean, I feel like these data sets were extremely small. And I think as long as you're balancing diversity in the data set with the size, seems like it usually gets better as you add more, but hard to say exactly. And then Dustin asks, how can we calculate the maximum amount of image data we can use based on how much VRAM we have available? So let's say I want to train LoRa locally and only have 16 gigabytes. It's a good question. Usually with these LoRa models, since you're only training a small subset of parameters, you can take like the full model parameters, assuming that you're training in like FP16. That means you would just like double the number. So if the language model and the vision model both took up like 7 gigs or had 7 billion parameters, then you should be able to train on a GPU with 14 gigs of VRAM. Yeah, Kenneth, did you have any other thoughts there? So it's probably a couple different factors, including batch size, image size, precision, etc. Cool. I will kill the recording so we can do a little offline chatter, but thanks everybody for joining. Hope this was useful and hope it inspires you to train some of these models on your own, because it doesn't take that long and a pretty small data set to get it going. Thanks everyone.